Thanks, Shoshana, and hi, everybody. I'm really looking forward to the questions at the end of this. I see this lecture as kind of a vehicle for generating questions and discussion. So yeah, I'd like to talk today about AlphaFold and other high accuracy prediction methods and how they've changed everything in structure determination of macromolecules. And at the same time, they've changed nothing. And they've changed everything because the high prediction accuracy of parts of macromolecules gives a bootstrapping for structure determination that's just amazing. And so this changes the way that you would approach structure determination today compared to yesterday. But nothing, because at the end of the day, the structure determination is still required, experimental data is still required because the predictions are not complete and they leave out many things and they have still many errors in them that we still have to fix, and we need the experimental data to do that. So here are the things that I would like to do today. First, I'm going to talk about how AlphaFold models are great hypotheses for protein structures. If you don't take anything else away from this talk, I want you to remember that part. They're great hypotheses, they're not the answer. Then I'm going to talk about how AlphaFold models or other advanced structure determination methods or structure prediction methods, I'm just using AlphaFold as an example for all of them, can really help you jumpstart structure determination of macromolecules by X-ray or cryo-EM or other methods. And then I'll tell you something that you may not know yet, that you can improve the modeling process itself by incorporating information from density map in an implicit manner. And then last, I'll get to the perhaps most important part, which is how AlphaFold models allow a completely new workflow for structure determination, a new way of thinking about how to go about the process of structure determination. So let's start off with AlphaFold models are great hypotheses. So let me just remind you about the aspects of machine learning prediction methods that I think are very important in discussing what they're good for and what they're not good for. So I'm not going to talk a lot about the details. I'm going to talk about the concepts. And that's going to be true for this whole lecture. I'm going to focus on things that are conceptual that don't really depend on any particular software that you can apply to your software or somebody else's software. And our software is just an example. So training for structure determination, for structure prediction. What do you have available when you're trying to do your prediction? You have a sequence of a particular macromolecule protein, a multiple sequence alignment, showing the relationship between that particular sequence and other sequences of proteins that are found in nature and therefore presumably fold as well. And similar proteins are thought to fold similarly, similar sequences are generally fold similarly. So we're going to be using that information. And we have, in our training, we're going to have a three-dimensional structure from the protein data bank. And this particular picture is 3MJS, one of the chains. And actually, I'll use that in a lot of parts of this little talk. Now, there are some 180,000 proteins that were used in the training for AlphaFold. So there's a lot of data that went into this. That leads to 21 million parameters. When you do the division there, actually, that's a lot of parameters given the amount of data that's present. And you could even imagine that a lot of the information in those 180,000 structures could be embedded in those parameters. So that's just something to keep in mind, that this isn't like a set of minimal parameters that knows everything. It's a lot of parameters. Okay, so you do that, and then now you can turn it around and do a prediction. You got a sequence, a multiple sequence alignment,
yeah,
something
in the US.
Particular. And then we can take our 21 million parameters And I'll mention this a little later, focus attention on important aspects of the structure, parts that may be close, and carry out and calculate a new prediction for this particular structure. And the green and pink structures aren't quite the same, and we'll be talking about that later. Okay, so now let's
we have a problem.
There we go. Okay, I unmuted myself now. Now we're okay. So in addition to the three-dimensional prediction of the structure, we end up with confidence estimates by residue for each residue in the structure. That's very helpful because the prediction is therefore giving a prediction of its own confidence, and that prediction of confidence can let us know what parts are likely to be accurate and what parts are not. And these confidence estimates are pretty good, but they're not perfect. And I want to emphasize that because these are people are tending to use them as if they were like a very accurate confidence measure, but they're not. They're the correlation between confidence estimates of accuracy and the true accuracy is about 75%. So if you think of a scatter plot with 75% confidence correlation, it's not that great. It's good, unbiased, but not perfect. Okay, so now let's talk about what information is going in here. The multiple sequence alignment is a very important part of the information going into a particular prediction, although it's not the only important thing. The key aspect of multiple sequence alignments are that residues that co-vary, that tend to change together in varying sequences, often are close in three-dimensional structure. And that is the reason for that is that things that are close in three-dimensional structure may touch each other, and changing one may change the environment for the other, so they tend to co-vary. A second aspect of the multiple sequence alignment is that all the sequences in the alignment should be compatible with the same structure. That's a very important piece of information. Given that multiple sequence alignment is an important aspect of the information going into AlphaFold, for example, the sequence coverage, the number of sequences that are present in the multiple sequence alignment for a particular position affects the confidence, how well the structure can be predicted. So in the lower part of this figure, the left-hand side of this sequence has a very high sequence coverage, and the right-hand side has lower sequence coverage. In the lower right-hand corner, the confidence is higher on the left side than in the right side. This is the same structure I showed you before. And here's the picture of the deposited structure in pink and the AlphaFold prediction in green. And the left-hand side of the picture corresponds to first 100 residues, which had very high sequence coverage. And the predicted model is very similar to the deposited model. The right-hand part has lower sequence coverage and is less accurately predicted. Now, AlphaFold models are very accurate where the sequence coverage is very high. And this is showing a piece of that structure superimposed on the deposited model. And what you'll see is that many of the atoms are like right on top of each other in these two models. So many parts of high confidence regions are extremely accurate. And they may even be more accurate than crystal structures or cryo-EM structures if the data was relatively low resolution in these parts. So that's an important aspect, and that is the thing that is incredibly exciting. There are some significant limitations, though. in particular, so far, the high quality prediction methods are only for protein. So we don't get the water, you don't get the ions, you don't get covalent modifications, carbohydrates, ligands, no DNA, no RNA. So that's part of the macromolecular structures, but by far not all. These prediction methods are trained on not necessarily well-filtered databases. So AlphaFold is trained on essentially everything in the PDB that's a macromolecular structure that's experimentally determined. And so the parameters might include some systematic errors. So that's good to keep in mind. And in the predictions, there's not that much information about residues that are far apart. So in crystal structures and in cryo-EM structures, once you have your structure determined, the distance between two residues that are very, very far apart in the structure can be very accurately determined, because the structure, the map, is a fixed map and it reflects the distances throughout the map. A predicted model might have small distortions everywhere, and so that by the time you get to a residue that's very far away from another, the exact distance between those two might be not that accurate. And we'll see sort of an extreme example of that in a moment. So here's an example of limitations. So this is an AlphaFold model for PDB entry 6TE3, and Tristan Kroll took that AlphaFold model and rebuilt it with his Isolde program. And the AlphaFold model is in blue, and the density map for this structure is in the blue mesh. And the AlphaFold model has a few problems. It put at leucine 710 an uncommon rotamer, so an uncommon conformation of the side chain. And in this particular density map, it doesn't fit the density that well. But it's a very high confidence residue, 0.97. So 1 is perfect. Tristan rebuilt that residue with Isolde and put in a common rotamer, and it fits the density perfectly. So keep in mind that AlphaFold models are great hypotheses. They're not the final answer. Here's another example reflecting the local versus long distance relationships. So here's PDB entry 7BGL. It's a multi-domain ring. And so we've predicted that with AlphaFold, and here's the AlphaFold prediction. And wow, you say, that's really terrible. Well, actually, yeah, it's terrible in that there's huge overlaps. But let's look in a little more detail. Let's take one chain of that AlphaFold model and blow it up. And we'll see, yeah, it overlaps badly with neighboring chains. But if we look at just that one chain and compare it to the deposited one chain, it's actually pretty good. This one isn't perfect, but it's pretty close. So the local relationships are much better than the very distant ones. Once again, these models are great hypotheses. So what can we expect from these high confidence prediction methods for proteins? They're great hypotheses. Parts of them are accurate. Parts are completely wrong. And the confidence measure is helpful, but it may not fully reflect the accuracy. Okay, so what can we do given these great hypotheses for macromolecular protein chains? Well, they can really jumpstart structure determination. So let's see how that works. So here are the things we can do. Those confidence measures, I told you they're not perfect, but they are good, and they allow you to prune away the worst. So you only have to look at the good part. And this works pretty well. the high confidence parts are often very accurate. And this one's a little subtle, but these predictions are much better than a homology model because they have essentially no errors in register. There aren't any insertions and deletions in the sequence, and they very rarely make a register error. So homology models often have short or even long register errors because there were insertions and deletions and it wasn't quite clear how to shift the sequence in those regions where there are insertions and deletions. With these high confidence prediction methods, is not a big problem. So that's a really big deal and is very helpful for rebuilding models. So here's an example. And this is a real one. Jamie Wallen had sent me a structure, actually sent it to Pavel Afanin in the Phoenix group 2 years ago, and said, I'm refining this structure and I can't finish it. It just doesn't seem to work right. And so there were a couple problems in the end. And one of them was the parts of the structure that were missing. So here's a structure, the status of this structure as of last fall, and it was missing 2 segments from 118 to 128 and from 139 to 147. And here's the map. So this is it's an okay map, but in this region it's not that good, and it's a little hard to see how to connect 118 to 128 and 139 to 147. Maybe you can picture how it would work. But here's how we do this today. We're going to say, let's generate an AlphaFold model for this structure. And let's just superimpose it on here. So I did this, and there's the AlphaFold model in red. And you can see that most of it just superimposes incredibly closely on the structure that Jamie had already determined. And it provides a super hypothesis for how to connect 118 to 128 and 139 to 147. So that's our hypothesis. And now let's test it. It's easy. We just look at the map. And wow, this is fantastic. The hypothesis fits the density map just incredibly well. So this was a great hypothesis. It was right. And so now Jamie took that and just refined it, and that worked great. And now the structure is a much better structure. And now the quality metrics, R factors, are in the range that you would expect for a structure at this resolution. So that was a really nice example of how AlphaFold can help. Others have used AlphaFold in lots of ways, molecular replacement. Here's a paper from Jim Hurley's lab where they just illustrate what's good and not good about the AlphaFold models. So this is 7JTL, has 2 chains, and the blue is the AlphaFold prediction. And you can see that some parts of it are a little different than the correct structure, and some parts are very similar. He used molecular replacement on that, and some parts are very accurate, and a lot of the side chains had wrong conformations. And some parts required actual rebuilding. This is typical. This is generally how it works out. So the AlphaFold models are great hypotheses, but they're not the answer. Here's a cryo-EM example, the same one I've been showing you, where the AlphaFold is very accurate in most of it, but not in the part that had relatively few sequences that are similar. So what can we do with the cryo-EM situation? In the cryo-EM situation, let's trim off the low confidence part. So we did that. So we didn't trim off the bad part. We trimmed out the low confidence region, which happens to be the bad part in this case. And then we're going to take the remainder and we'll dock it into the density map from cryo-EM. And then we'll trace the remaining loop. So we'll use the cryo-EM density to trace the chain in the part where we didn't know where it was. And the nice thing here is because we have the sequence register all right, we know exactly how many residues and what residues are supposed to go into that loop. So there's the trim model, there's our rebuilt model with the loop. Great, so we can jumpstart structure determination. And now I want to tell you something that's really kind of amazing, that you can actually make the structure prediction tool work better by including information from that density map. And I'll show you how we can do that now. So here's the picture I just showed you with the AlphaFold model that's been rebuilt in blue, and the right answer, the deposited model, that's in pink. Now that rebuilt model is actually not that great. You can see it doesn't have such a nice beta loop out there. And maybe, however, that rebuilt model has some information that could be used to feed into AlphaFold to make a better prediction. So here's how we're going to do that. Normally, we're going to start with a sequence and a multiple sequence alignment, the parameters from training the model, and generate a prediction. So instead of that, the prediction then is poor in the loop region. So instead of that, we're going to do the same thing, but we're going to add a template. And what the template does is it gives two things: a set of possible backbone angles, which in this case actually aren't that good. And more importantly, it's going to allow the AI prediction tool to focus attention on residues that are close. So this template is going to say that the residues, the paired residues in that loop, are relatively close to each other. Focus attention on those in the prediction. And this is going to lead to a new prediction that's quite accurate and definitely better than the previous one. The amazing part is the new prediction is better than the template. So that means you might be able to do some kind of an iterative process, improving a template, getting a template, improving the prediction, getting a new template, getting a new prediction. This is very powerful and doesn't depend on any particular software, as I've been emphasizing. So here's an example of using a template to allow AlphaFold to focus attention on the right parts of the structure and improve a model. So in this example, we're going to do an AlphaFold prediction with no multiple sequence alignment whatsoever. We're only going to feed in a template, and we're going to a template and a sequence, and we're going to allow it to generate a new structure. So this is back to the structure from Jamie Wall, and this is a different version of the structure that was earlier. And this picture shows his refined model at one stage in this process, a little piece of it. And there are some problems with this model. On the left with the little arrows, you can see that the density doesn't exactly fit the model. And on the right, there's a side chain that's completely out of where density is located. And these big side chains usually go with density, so it's a little surprising. So we're going to do a prediction using this model as a template. And now we have a new AlphaFold model. And the amazing thing about this model is it's actually changed the register of this part of the structure. So now different residues are in the place of these two pieces of density that didn't fit very well before. The one on the left now is has a sulfur right at the big piece of density. And on the right-hand side, that phenylalanine is now moved over to a different piece of density. So it's more plausible where it is in this case. And once again, the new prediction is even better than the template. So this doesn't always happen, but it's not an uncommon thing, and it's an amazingly powerful result. So now we can apply this in an iterative way. We can generate an AlphaFold model. We can improve it by looking at the density map and rebuilding it. And then we're going to use the new rebuilt model as a template, iterate the process. So here's the example. Once again, this is the 7MJS, same one I've showed you all along. And this is just looking at the region where on the left, the model is good, the predicted model is good, and on the right, the predicted model is bad. So we trim it off the low confidence right-hand part, rebuild it, and here's that rebuilt model. It's not that good. It just kind of goes through the density in this particular case. And we're going to take that rebuilt model, feed it as a template, and generate a new AlphaFold model. And that model is a little better than the template. It's not perfect yet, but we can rebuild this one much more easily because the difference between the AlphaFold prediction now and the right answer is actually very small. You can see it's just a little bit of a rotation. So rebuilding that was trivial. Using that as a template, we get a new AlphaFold model that's very similar to it, and now it's almost right. Iterate that a couple more times, and now we have an AlphaFold model that agrees very well with the deposited model. And note that this AlphaFold model that I'm showing you in this picture is just superimposed. It's not refined in any way. So now, by using the map information from the density map, we've generated an AlphaFold model that has both short range and long range distances that are very accurate. So we've dramatically improved this particular structure. So to summarize, doing an iterative prediction and rebuilding process, you can rebuild that AlphaFold model with the density map. The rebuilt model improves the next prediction, and you can iterate to improve the model. Okay, so now, given all that, what are we supposed to do when we're trying to solve a structure by X-ray or cryo-EM? Well, this really does change everything in how you start this out. So here's a strategy now for how to think about and how to go about solving a structure. So the first thing you're going to do before you do anything else is you're going to get a prediction for every chain that can possibly be modeled. So you do that before you do any experiment. And now suddenly you have a very good idea before doing any hard work of how hard this problem is, what information you're going to have to start off with. And this allows you to think about, how am I going to solve this structure? What experimental information do I need in order to complete this structure? Because remember, this starting prediction is going to tell you something about what's known and what's not known, as well as a picture of the part that can be modeled. So this is just incredibly different than all the way up till now. Okay, so you have for every chain in your structure, you've got a prediction. You know what parts are likely to be good, what parts are not so likely to be good. So then you decide how to get your map. You're going to do cryo-EM, X-ray, NMR, whatever you're going to do to get some more information. So you're going to get some kind of density map in one way or another. And then you're going to use that map to improve or create, if you didn't get it, every chain in the model. And in the old days, if you had an X-ray structure, you would take that improved model and you would improve the map with it, with density modification if you had X-ray. Also in cryo-EM, now you can do a little bit of that with density modification as well. But today you're going to do it a little differently. Instead, you're going to take that improved model and you're going to generate a new prediction, and then you're going to iterate that process. So now you can get a better map and you can get a better model and you can iterate the process until you're tired of it. So overall then, you're going to predict the chains, you get a new map, you're going to place your model in the map, you're going to improve the models, get better predictions. So that's conceptually how you might want to go about this now. And let's just compare how we used to do this with how we're doing it, how we can do it now. So previously, maybe you had a homology model, or maybe you had no model at all. You got a map, you placed the model on the map, and you improved them as much as you could. And if you had X-ray data, you'd iterate that process and get a better map. Now with AlphaFold, you're going to get a predicted model that's going to be much better. Typically, you get a new map, you place them in the map, improve them, get a better prediction, you iterate that a few times. And what's the difference here? Well, number one, your starting model today is a lot better than it was a couple of years ago. So your predicted model is much better. Now you can do this cycles of improvement with either X-ray or cryo-EM data and improve the map, improve the model predictions. And because you can use the improved models as templates, there's more improvement every cycle by using those new models. So it's more powerful at the start and you get more improvement along the way. So totally exciting, and you're in much better shape than we were a year ago, 2 years ago. Okay, so how much difference does all this make? I'll just give you a couple examples. This one is 7-MLZ. It's a spike protein complex. And on the left side, the blue shows how good the AlphaFold initial prediction is compared to the brown deposited structure. It's pretty good, but these loops are not really quite right. It's kind of wrong orientation. After iterative building prediction, it's a lot closer. This is a relatively low resolution structure, 3.7 angstroms. And in this region, the map's not that good. So this is a much improved structure. And this is just to show that this is a lot better than kind of the old way of doing this. Like if you just had a map and you tried to model build into this map, the same structure, the upper left corner here shows deep tracer chain in blue, which is pretty wrong. Phoenix map to model in purple is even worse in this case. And the doc and rebuild using this procedure I just described is much better. You can look on the bottom, you see the maps. The map's not that good. So using this prediction method, you can generate a structure relatively easily. In this case, is quite accurate. And you might ask, so how much difference does all this iterative process make? So this plot shows on the x-axis what percentage of C alpha atoms are within the 2 angstroms of the deposited model. So basically how good they are for 25 recent structures using just the prediction alone and then superimposition. And the y-axis shows the percentage that are within 2 angstroms after the iterative process. So basically everything above the line got better by using the iterative process. So it doesn't make them perfect, but it improves them. Almost all cases improves them. In a lot of cases, it improves them a lot. This just shows that a little bit of detail for these structures. And this shows for each structure how good the initial model is in purple, and then after cycle 1, 2, 3, 4, etc. So what you notice here is that sometimes it all improves at the beginning. Sometimes it improves sort of steadily. Sometimes it doesn't really improve at all. So now the and nothing part. Well, after you've done all this automatic iterative building, where are we? Well, then it's really the same as always. You need to identify and fix errors. You're going to refine the structure. You're going to add covalent modifications. You're going to add ligands. You're going to identify alternative conformations. You're going to add solvent. You're going to estimate uncertainties. All this is just like always. So we got a big head start, but we still have to do a lot of work. We have tools in Phoenix for dealing with all these things. We have GUI tools that will use Google Colab to run AlphaFold, or run AlphaFold with a density map that will improve the model. As I described to you, there are GUI tools for trimming off the bad parts of model, uncertain parts of models and for rebuilding chains. We have in process, not quite in distribution yet, a new tool that will kind of do the same thing as AlphaFold with the density map, but for an entire structure, not just one chain. One last minute, just some observations about AlphaFold, and presumably Rosetta Fold and others will fall into many of the same categories, just in case it's useful to you. So the multiple sequence alignments or templates, their contribution to the information going into prediction is basically telling it what is close. So if you have a good MSA, you don't need a template. And if you have a good template, you don't need an MSA. They don't really need both. It doesn't help that much. And another thing is that all the inputs for AlphaFold basically are going in a table with one column per residue. That means that all the information, the MSA, the sequence, anything else that's going in, the information coming from your template is all linked specifically to each residue position in the structure. So what that means is if you have an incorrect alignment in your MSA, you're putting information in the wrong column. So that will make your prediction worse. If you have multiple confirmations in the structure so that different parts of your MSA coming from different structures that have different confirmations may yield very complex MSAs. And so down the road, it may be very useful to separate these out in some way so that you have an MSA that's really only representing one confirmation. I don't think anybody knows how to do that yet, but I think would be a very powerful thing if you could. Another corollary is that a template that cannot be aligned or not aligned correctly to a sequence are useless. And thank you for listening. And now I'm looking forward to a discussion about this. There's many people that helped with this, and the people in the Phoenix project have been fantastic. And many users have contributed in lots of ways to developing all this work. Thanks very much, and looking forward to questions.
Thank you, Tom, very much for this very, interesting and practical, guidelines of what to do, which is, really very, very useful and important. Now, please, we don't have too many participants, so I think if people have questions, they can actually, come up and ask them, directly. So please go ahead if you have any questions to Tom. He will be happy to answer, and we have time for that.
Hi, Shoshana. Hi, Tom. If I may, I'd like to ask a question. Is that okay?
Sure.
Yeah. Thank you, Tom, for a great talk. I had 3 questions. One was on, I think you said at some point to use the rebuilt models to improve your maps. I can see so for the crystallography, for the cryo-EM, I was wondering how you see that. Are you seeing to use the models as a template for the reconstruction, or how do you, where would you see that improve the map?
Oh, yeah. So in cryo-EM, one normally thinks of the map as being kind of a static result from the reconstruction. But actually, if you have any kind of external information, it is possible to improve that map. And one way is the way you described. You can redo the reconstruction using a model to help orient images. That's one way. We're not doing that. And actually, it's a very important technique that will eventually be a standard thing. Right now, it is rife with potential problems that involve bias, right?
Yeah.
So I'm not proposing to do that at the moment,
Okay.
although I do think down the road that is a very important thing that will be done. But we have alternatively another technique that also has potential problems with bias, but doesn't seem to be too serious at the moment. And that is, you can do density modification of cryo-EM maps that's somewhat similar to density modification of X-ray maps. And you can include information from a model in that process. We try to debias that density modification process with the model by generating an ensemble of models to use as, and from that ensemble of models, we generate model density, and then use that model density as a target for density modification. In practice, it seems that that works quite well for accentuating information that is correct in the map and not changing substantially information. That's not changing information to match parts of the model that are wrong. And probably that's because the parts of the model that are wrong end up being very different in different members of the ensemble. Parts that are correct tend to be the same in different parts of the ensemble. And so that ensemble density map reflects mostly the correct part. So that seems to work quite well for improving the maps. So that part of the iteration process is still potentially good. So in the examples that I showed you, we didn't do that. We only used, the iteration aspect was only a rebuilt model as a template for AlphaFold rather than improving the map itself. So that's just potential.
Okay. Yeah, and a bit related to that, and again, there's the issue of how to deal with the bias, but I could assume, I mean, these regions like you showed where the density is less clear, that is, I mean, well possible that this is a signature of true conformational ensemble in the structure. So could you use the AlphaFold template, so the conformations that it predicts, you know, to guide 3D classification, but how to do so with avoiding bias again?
So yeah, in principle, one could do that. One of the things you can do with AlphaFold is you can, if you supply it with a template, it will try to build a model that's somewhat similar to the template that matches all the geometric criteria that it knows about, basically. And so you could potentially do something that along the lines of what you're thinking about is, suppose you have a loop that, or some part of the molecule that seems to be in different conformations. Okay, so then you build with whatever tool, a number of different conformations for that region. You use each of those as an AlphaFold prediction and generate a number of models that are each internally consistent, that could represent what's going on there. And then you would go back, like you're saying, and take those models and use them as seeds for some kind of focused reconstructions, or classification rather, and then focused reconstruction perhaps. And then you might be able to separate out the different classes. So I'm hoping that down the road, yes, people would do things along the lines you're thinking. Okay.
I have a further question, but I'll first give other people a chance to ask. I don't want to hijack the discussion.
There is one question on the chat, if I could read it, and maybe others will follow. The question is, in your personal anecdotal experience, how good is template-based prediction with longer loops, for example, longer than 20 residues? Would you trust the predicted model if the density was only good enough to mostly but not fully trace the backbone using just the brain power and imagination?
Yeah, it's actually a great question because it's asking whether we think that an AlphaFold prediction with some kind of information going in there that's a little bit extra, what kind of confidence we have in the result. Mm-hmm. And so my answer to that is, I don't know the answer, of course, right? So my gut feeling, as you asked for, is that if AlphaFold, when you do this, so you're going to feed in some kind of approximate template, and if that template is really bad, AlphaFold basically is going to ignore it. It's not going to do much with it. But if it AlphaFold, in my experience, if you feed AlphaFold something that is close to the right answer, it will jump to the right answer, and it will know that it got the right answer. If you feed AlphaFold something that's totally wrong, it will give you something that's totally wrong, may or may not give you what you gave it, and it will generally know that it's wrong. And giving it the answer could be either of two things. You could be giving it a template in this context, or you could be giving it MSAs, multiple sequence alignment, in the same answer. If you gave it a garbage multiple sequence alignment, it will typically not give you a good answer, and it will typically know that it didn't. If you give it one that's very good, it has much information. And what that means, right, is if you have a multiple sequence alignment that has very deep, has a lot of information in it, that means AlphaFold can know what things are close to each other. It doesn't tell AlphaFold that this side chain is in this conformation or anything like that, right? It just tells it what is close. And that's enough to get it in the right local minimum, and then it can jump to the answer. So that's actually, I didn't emphasize that enough in this talk, is that AlphaFold seems to be incredibly good at getting from a close confirmation to a correct confirmation. It's not that great by itself at getting from something that's far to something that's close. That's why we need to give it a template that's something like the right answer, or an MSA that's something that's very, very good. So bottom line is, no, I don't think you want to take any of these predictions for some loop and say this is the answer. But I do think that if you, whatever information you put in there and whatever prediction it comes out with, if it comes out with a high confidence, then it's likely to be a good hypothesis. But you still need to ask some kind of questions about that hypothesis to evaluate whether it's really right.
Thank you. Any other questions?
Okay, I
Yeah,
still
go
have
ahead.
a question.
Go ahead.
Yeah,
Go ahead.
It's
thank you.
an opportunity. Go ahead.
Yeah, I was wondering about inclusion of machine learning into Phoenix Refine. I mean, you touched on it a little bit, and then mostly related to AlphaFold building. But I've recently been struggling with a refinement where the most painful part was getting a ligand CIF file of a complex ligand correct. And I wonder if this is an area where machine learning can probably certainly do it better and probably faster than I do it manually in creating these geometry files.
That's a great one. So that particular example, no, we have not, we're not working on that one yet. So your question is, as I understand it, is there are a lot of things in structure determination that involve taking some information that you've got, partially built model, some ligand that's in some conformation, and turning that into the pieces of information that are necessary for actually doing a refinement or for doing feeding
to get the geometry. So the ligands are organic chemistry, and it's sp2 or sp3 bonds, and the bond distances,
right,
you know, they're arranged. And so I now have to manually go in for these complex ligands, and there is tools out there, but I mean, this was a pain setting it up, particularly if it's a ligand which is a component of, I mean, it had fatty acids bound to sugar, etc. So I can do it with things like prodrug, and then it's a completely new entity, but that's suboptimal because then it's one by one. So there is some systematic, I mean, it's ester bonds and amide bonds in there. So it would seem to me that machine learning from just looking at an organic chemistry database would learn about what bond angles to expect and not, and to build up these geometry CIF files. That is a possibility.
Yeah, I think it's a good idea. So I mean, right now we have the elbow tool in Phoenix that tries to do these things. And it uses, semi-empirical quantum QM calculations to try to do the calculations at the end. But surely one could kind of rebuild all the database that's in that in an automatic way. It seems entirely possible. And, I'll actually mention that to our people and as a suggestion for what a machine learning thing that we could work on. We have a lot of machine learning projects that we're just starting now, actually. The main ones are how to place ligands. That's actually the first one that people are focusing on right now. How to place waters, how to place ligands, but generating the restraints for ligands, I hadn't thought of that, but I think it's a very good one. So yeah, I will suggest that.
So, I mean, and indeed, I used Elbow, and Elbow works great, but then Elbow, it does assume it as one residue, the ligand, but the ligands, I mean, many of these ligands are multiple residues. And if you look at the fatty acid as one residue that's connected to a sugar, which is another residue, etc.
Yes.
That would, and then you have to manually edit the CIF file. And if this is, a multimer, this was a rather painful.
Yes, no, I can imagine. Just a comment on that is that all the machine learning methods work really great if you have a lot of examples that are right. And this kind of, so your case involves some generalization, which is a little tricky.
True, but you could still have then the experimenter look at it. I mean, it's still ester bonds, amide bonds, it's sugar puckers. So I think there are a lot of examples out there, and it will probably recognize what the bond is if I place it close enough in 3D space, just a little bit like Elbow does now, but then sees it. If I give it different residue numbers, I could imagine that the machine learning will recognize what covalent bond is going on there between the two residues.
I think it's a great idea.
Really important tools, technical aspects that, will facilitate your life.
Yes, exactly.
Great. So any other questions you have? Anyone? It's an opportunity. Ask.
I have a question.
Yeah, Anastasia, go ahead.
Hi, thank you for the great talk. So I was wondering if you ever tried to iteratively refine a protein that's in two close but real conformations. So we know that AlphaFold is biased towards the apo or holo structure if you just feed it the MSA. But if you use a template, can you actually compensate for that bias, or do you think you will end up with one of these?
It's a great question, and so I haven't actually done it, but yes, I think you should be able to compensate for this by putting in a template that has a rebuilt conformation that corresponds to the one that's in your structure, as opposed to, say, the APO or whatever. And that is a problem that AlphaFold tends to give you consistently one conformation when there are known multiple conformations in the database. Another approach to that is to separate out the multiple sequence alignments and have a set of multiple sequence alignments that all focus on one conformation. So that's another possible approach to solve the same problem. And as I said, I don't know how to do that exactly yet, but suppose you, just to speculate on it, let's suppose you had in the PDB, you were able to identify classes of proteins that are related proteins, that one set of sequences has this conformation, another set has another. And if you're able to classify those in some way, then you might be able to do all the downstream related sequences and classify them into, these are more likely to be this conformation, these are more likely to be that conformation. Then you could feed those separately as MSAs to AlphaFold and get different predictions. So something along those lines might work.
Yeah. we are just looking into this by, you know, starting from the conformations first, and, you know, kind of charting the conformations of protein family, and then clustering these conformations, and then going to see how the sequences, you know, what in the multiple sequence alignments that are corresponding, you know, can you use that, you know, to try to, you know, disentangle your sequences, as you say.
Yeah, that would be great. Yeah.
Trying to do this.
Yeah, but it doesn't seem easy, but it would be
No,
really
no,
great
no.
if you could do that.
Okay, no more questions. Great talk, great discussion. And thank you, Tom, for joining us today. And
very happy to
I
have
hope
done it.
you stay in contact, you know, to try to solve
Indeed.
some of these problems, no? Okay,
Yes.
thanks to
Great. Thanks for all the
everybody.
questions.
Yeah, thank you.
Okay.
Have a
Bye bye.